The final method of proof that we want to look at in this course is proof by induction. This is where we show, so we get given some formula, let's say, like show that the sum of 1 to n is this formula, maybe n plus 1 over 2 or something like that. That's one of the examples we'll look at in a moment. What we're going to do is we're going to show that it holds for at least one case, and that's usually what the base case, so we show it for n equals 1, for example. Then what we do is we assume that it holds at an arbitrary state. So we assume that it holds at step n, and then we say that if it holds at step n, it must be true for n plus 1. And so in particular, since I showed that it was true at least one stage, I can apply this iterative procedure and it must be true at all stages. That's the method of induction. It's very simple. It's the same procedure over and over again. And so we'll look at a few examples and you'll be convinced in a moment of how simple it is. Okay, let's look at these examples. So now let's look at an example of a proof by induction. This is where we have some type of formula that we want to show is true for every natural number. The way we do this is by showing that it holds for the first case, assuming it holds at some arbitrary stage, let's say stage n, and then using that induction hypothesis to deduce the next stage. So we want to show that for all natural numbers n factorial is less than or equal to n to the n. The base case occurs when n is equal to 1. This is the first natural number, so for n equal 1, let's see what we get. Well, n factorial is now 1 factorial, but 1 factorial is just 1. On the other hand, we see that n to the n is 1 to the 1, which is of course just 1, and since 1 is less than or equal to 1, this verifies the claim for this first case. Now assume the statement is true for n. We want to show that the corresponding statement for n plus 1 is true. The way we're going to do this is by finding the n factorial is less than or equal to n in the statement n plus 1 factorial. We want to find an n factorial in there. What we can do to pull out an n factorial is to write n plus 1 factorial as n plus 1 times n factorial. But since n factorial is less than or equal to n to the n, we see that n plus 1 times n factorial is less than or equal to n plus 1 times n to the n. Now, n to the n is going to be less than or equal to n plus 1 to the n, and so n plus 1 times n to the n is less than or equal to n plus 1 times n plus 1 to the n, and that's just n plus 1 to the n plus 1, which is exactly the statement that we're trying to prove in the n plus 1 case. That completes the proof by induction since we showed it was true for one stage, and then we show that we can get to the next stage if we assume it holds in the previous stage. That's how an inductive argument works. Let's look at a second example. Let's try to show that the sum of the first n natural numbers is equal to n times n plus 1 over 2. Again, the base case, since we're working over the natural numbers, is going to be 1. And we see that for n equals 1, we get 1 times 1 plus 1 over 2, but that's just 1. And of course, the first integer, when you add it up, is just 1. So this verifies the claim in the base case, or verifies the claim in the case when n equals 1. Now, assume that it holds at n. We want to deduce that it's true at the next stage, at the n plus 1 stage. And remember, the way we're going to do this is to find the current stage expression in the next stage expression. So let's write the sum from k equals 1 to n plus 1 of k, which is just a way of writing the sum of the first n plus 1 natural numbers. We can write that as n plus 1 plus the sum from k equals 1 to n of k, because if I add up the first n plus 1 natural numbers, then that's just the sum of the first n natural numbers plus the n plus 1th natural number. So by the induction hypothesis, by assuming it holds for n, we know that this is equal to n plus 1 plus n times n plus 1 over 2. Now if we write this over the same denominator, we see that we get 2 times n plus 1 plus n times n plus 1. But this is just equal to 2n plus 2 plus n squared plus 2n over 2. And we can factorize that as n plus 1 times n plus 2 over 2, which is the corresponding statement in the n plus 1 case. Okay, to see if we understand these induction arguments now, try the following practice problem. So try to show that 2 to the n is less than n factorial for all natural numbers n which are greater than or equal to 4. A solution to the practice problem. So remember, we want to show that 2 to the n is less than n factorial for all natural numbers n which are bigger than or equal to 4. The base case is n equals 4, in which case we see that 2 to the 4, that's just going to be 16, while 4 factorial is going to be 4 times 3 times 2 times 1, which is 24. And so since 16 is less than 24, this verifies the claim in the base case. Now suppose that the result is true at the current stage, so suppose the result is true at n. We want to show that the result holds for n plus 1. So we'll write 2 to the n plus 1 as 2 times 2 to the n, but we know that 2 to the n is less than n factorial, and so 2 times 2 to the n is less than 2 times n factorial, but this, by the induction hypothesis, is less than or equal to n plus 1 times n factorial. But 2 is certainly less than or equal to n plus 1, and so 2 times n factorial is less than or equal to n plus 1 times n factorial, but this is exactly n plus 1 factorial.